We're going to cover kinematics today in our first video here. This is the first content unit that we're going to look at in this course, and almost any physics course it'll be the first content you'll start with for a course focusing on Newtonian mechanics like this one. Kinematics is almost always started because it's easy to understand conceptually and a great way to introduce us to 3 or 4 of the main ideas we'll focus throughout this course. That is rearranging and solving equations, which once again I'll state, don't focus your efforts on. Maybe 20% of the AP exam and my exam will be those type of problems. You need to know how to do them, but that should not be your key focus. Interpreting and creating graphs is what this video will focus on. You really need to make sure that that's one that you're going to look at, as well as getting a key conceptual understanding and what we'll call vector addition we'll look at in 2D kinematics. But anyways, today we're going to focus on the graphing aspect, and to get an understanding of that, I'm going to rearrange and rewrite some of our key kinematic equations that are real important. So the first one is going to be the first one listed on your formula sheet. I'm going to write it a little bit differently, and we'll see why in a bit. We're going to write change in velocity, which remember is always final velocity minus initial velocity, equals acceleration multiplied by time. And the second kinematic equation we'll write, I'll also rewrite this one just a bit differently than you're used to seeing it, but we're going to write it as final distance or final displacement equals 1/2 at squared, acceleration times time squared, plus initial velocity times time, plus initial position. Now there's a reason that these two are first kind of kinematics, and they do relate very closely to the graphs. And so the first one we're going to look at is this one right here. And what we're going to look at is a position versus time graph. And so for a position versus time graph, if we have constant positive acceleration, it's going to give us a graph that looks something like this. Normally if you're creating a graph, we'd have labeled units, we'd maybe have various points plotting a best fit curve and an actual scale, but we're just getting the general ideas here today. Now, we say, well, what type of graph is this? Well, we see this curve and we see this equation, and you should see a correlation, because what mathematical equation gives us this parabolic curve like this? Well, it's y equals ax squared plus bx plus c. And if we look at that, we see, what do we have here? Well, ax squared, a is 1/2 a, x, we plotted time on our x-axis, y, of course, is our displacement here, bx, that's our initial velocity times time, plus c, is our initial. So we have a relationship here that's going to be really, really important. So, very important here. Well, we do need to know one key thing about understanding what's going on in this graph. And the most important thing about going on this graph is to understand what the velocity is. We can use this graph to determine, is the car speeding up, is it slowing down, is it accelerating in the positive direction, negative direction, all things like that, very, very important. Well, the key idea for this graph, one of the main things you need to make sure you memorize, is that the slope of this line is always going to be equal to the velocity. Now this is a curved graph, so our slope of the line is going to be our tangential slope at various points. This is an accelerated graph, so we can see that we have an increasing velocity as time goes on, right? Our velocity starts out very shallow, it's a slow velocity, but we're speeding up, speeding up, speeding up, because our position is changing over a faster rate. So this is the key idea for velocity. And the slope, remember, is position divided by time, displacement divided by time. And velocity is distance divided by time, rise over run, giving us our value for velocity here. So kind of an understanding of the relationship between these equations, where this graph comes from, where this equation comes from, and this is a key idea for understanding the position time graph. Now next, we see this one right here, change in velocity equals acceleration times time. You may notice that this may look like a y equals mx plus b equation. If we move initial velocity to the other side, we get the plus b instead of change in velocity here. So what is that going to look like if we graph velocity on the y and time on our position? Well, we should see our slope, our m value, should be our acceleration here. So let's take a look at what that is. A velocity time graph usually going to look something like this. These two graphs are graphing essentially the same motion, a constant increasing velocity, a constant positive acceleration. And so we see y equals mx plus b, with essentially our y is our velocity. So velocity equals acceleration times time plus initial velocity. Initial velocity is our starting velocity here. That's our intercept. Our slope is going to be the acceleration. So that's a key thing for this graph, to know that the slope here for a velocity time graph is our acceleration. There's actually another bit of important information we need to know from this, and that is the area under the curve is going to be equal to our displacement. So if we want to know how far we've traveled, what is our total displacement, we're going to need to find the area under the curve, and that'll tell me how far we've gone. Essentially, my change in position from this graph, right? So let's look at the third graph, probably the least important graph. The acceleration time and velocity time are by far the most important. But our third graph here that's going to be real important is an acceleration time graph. And because we're almost always going to be looking at constant acceleration, your acceleration time graph is almost always going to be a flat line, or it'll be 0 for constant velocity. The important thing to know about this graph is our area under the curve for our acceleration time is going to be equal to my change in velocity. So you'll notice there's a pattern between these three, right? And if you ever take calculus, you'll find a few relationships between these as well. But this is an algebra-based course, so we won't worry about derivatives and integrals. But what you'll find is the slope will always take us to the next level up. So the slope of a position time graph is our velocity. Our slope of a velocity time graph is our acceleration. And if we look at area under the curve, it'll always go the opposite way. The area under the curve of acceleration time graph is velocity, and the area under the curve of this graph is displacement. So those are some key things you need to know about these graphs, but make sure you're also able to understand and be aware of what's happening physically in these situations, right? Be able to answer questions like, well, where's it speeding up? Where's it slowing down? Where's it have positive and negative acceleration? Remember, those are not the same thing as speeding up and slowing down. Where is it stopped? Where is it changing direction? These are all questions you need to be able to ask for really any graph that you're going to see. So that's definitely something you should practice. And that's all for